Welcome. This question says a sinusoidal wave has an amplitude of 4 meters. It has an angular wave number of 2.3 radians per meter. It has an angular frequency of 1.7 radians per second. What is the y-axis displacement of a point located 2 meters to the right of the origin at times t equals 3.5 seconds? And let's visualize for a second or two. So here's our y and x axes, and here's our wave at times t equals 0, and we're imagining ourselves at a certain distinct position away from the x, and we're saying what's that y, but we are not doing it for t equals 0. We're going to do it for a different time. And so we imagine at some later time, what will our wave look like? And our wave will look like this. So then we say, well, now at this position and at this new time, there's our y-axis intercept. So our y-axis is value, displacement is determined both by where we are on the axis, on the x-axis, and also what time it is. And what I said to you in other little videos and in class is that we can think of this as being, let me clean this up. We can think of this as being an exercise where we find our position of x, and then we take into account the effect of time by looking, if the wave is moving to the right, by looking to the left. And so we find this would be our value at position x at time t. And the kind of mantra is, if the wave is moving to the right, then we can see the future of the wave experienced at position x by looking to the left, along the wave to the left from position x. So the further I go along the wave, the further I'm going ahead in time, because it's going to take longer and longer and longer for this bit to eventually make it there. So if this is the y-axis displacement at time t equals 0, well, this is the y-axis displacement at time t equals 5 seconds. So that's the philosophy, and we did that in an expression before, and what we found in that expression was that it was good to say y equals 2 pi sine, y equals a sine 2 pi x minus vt over lambda. And basically, there are other questions that use this expression. But we're not given v, and we're not given lambda. We're given these other weird things, angular frequency, and well, we're somewhat familiar with that, but angular wave number, that's probably new to us. And everything in physics is introduced to make life easier, so these things will make life easier. And it's just unfamiliarity. So let's spend a little bit of time on that. If I think in terms of an oscillation, and I think in terms of a wave, there are some, and both of them look like a sine wave. In one case, this is y versus time. That's this thing bouncing upwards and downwards, and that's an oscillation. And in the other case, This is y versus x at an instant in time. And this is a wave. And unfortunately, they look very similar. I can point out to you the fact that the distance from there to there is a period. This is a graph of one oscillator's history in time. And I can point out to you that the distance from there to there is a wavelength. This is a picture, a snapshot of a whole bunch of oscillators in time. But it's easy to see how you can get these two guys confused. And so we've got to be a little bit careful about them. Let's talk about this period for the oscillator and the wavelength for the wave. After a while, we got sick of dealing with very small periods for very high frequency waves, and so we invented the frequency in hertz. And then, for a reason I'll get to in a minute, we decided to talk in terms of angular frequency, and that was omega. So we started off with period, and then we started talking about, if you like, linear frequency, and then we started talking about angular frequency. And we found this angular frequency, which is in radians per second, was quite useful. This is, of course, in hertz, and this is, of course, in seconds. On the wave side, looking over here, well, we have our wavelength, and after a while people started saying, well, just as the frequency is how many cycles do you have per second, so you could talk about how many wavelengths you have per meter. And so we developed the wave number. It's a little curly V with a squiggle on top, and this is the wave number. And if the wavelength is in meters, this is in 1 over meters. It's how many of these things do we get in a meter. Just like actually the hertz is 1 over seconds traditionally. We call it hertz because we named it after hertz, but it's fundamentally 1 over seconds. And by the same analogy, what we find it useful for, we find it useful to actually talk in terms of not so much wave numbers, although we can do. We talk in terms of angular wave number, which is a K, which causes some issues because it's the same symbol we use for spring constant. You know, so feel free to kind of put a little bit of decoration on to make it stand out when you're writing things down. And this is going to be in radians per meter. So it's really good to kind of maintain this, if you like, this orientation of these analogies and try and get clear on what things are, especially the units. Okay. Why do we like omega and we like K? And well, there's various reasons, but one of the reasons is, let me see if I can clear this up a bit. One of the reasons is that, I'm not sure I should have done that, never mind. One of the reasons is that, I'm going to clean this up and do this again. Instead of looking at a certain position, X, and then looking backwards to take into account the T, we could recognize the fact that simple harmonic motion can be thought of as a component of uniform circular motion. And so one wavelength is like going around a circle once. So if we are 1.5 lambda along here, we are, well, 1.5 times 2 pi radians around here. So we get the same we get the same effect, our y-axis displacement, we get the same values by looking not in terms of a sine wave, but in terms of a phasor diagram showing the circular motion, of the uniform circular motion that mirrors the simple harmonic motion. So whereas this expression is designed to be used with, if you like, linear information, like x position and wavelength and the velocity, there's another expression which is a sine kx minus omega t. Again, minus if the wave is going to the right, positive if it's going to the left. And this is an expression. Let's again do some erasing here. So now I'm going to imagine my journey, and I'm going to say, okay, I start off, and in a certain distance, well, if k is in radians per meter and x is in meters, this bit here tells me how many radians have gone round. So rather than how far have I traveled along the x-axis, I can say how many radians have I gone round. So I went by 1 pi, 2 pi, 2 and a bit pi. Sorry, yeah, 1 and a bit wavelengths is 2 and a bit pi. Same information, just expressed in angular terms. And then over here, I did this thing where I took the time expression into account by basically saying, well, you know, what's going to happen at this point in the future, I can see by going to the left to an extent dependent upon the time. Well, if that is in radians per second, which it is, and that is in seconds, then I have a modification of the number of radians. So I don't know if you can see it, but you're basically doing the same thing. You're looking to see the effect of your position on your y displacement, and then you're modifying it by the effect of time. And if the wave is traveling to the right, then what will happen at your point of interest can be seen by looking to the left along the wave. We're doing the same thing here, but in angular terms. So having said all that, let's look at our expression. Let's look at our situation. I'm gonna draw it out. So it says, what do I know? A sinusoidal wave has an amplitude of 4 meters, so A is equal to 4 meters. That's basically from here to here. That's my amplitude. And it has an angular wave number. This is my angular wave number is my K. I like to put little things on the ends of 2.3 radians per meter. It has an angular frequency of 1.7 radians per second. And then what is the y-axis displacement? At x is equal to 2 meters and t is equal to 3.5 seconds. What I do then is I come along, this is really the easy bit, A is equal to 4 sine k 2.3 times x, x is 2, minus omega, omega is 1.7 times t, t is, what was t? 3.5. So y is equal to 4 sine, that's going to be 4.6 minus, what is 1.7 times 3.5? 1.7 times 3.5 equals 5.95. So y is equal to 4 sine 4.6 minus 5.95 equals minus 1.35 minus 1.35. That, of course, is radians. So y is equal to, let's check we're in radians, and we are. So I'm going to say sine minus 1.35. Remember to use the little negative sign, which is the sense, rather than the negative sign, which is the operator. So it's sine minus 1.35, enter, and then times 4, which is minus 3.90, minus 3.90 meters. And there we have it. So it's a different way of looking at waves. In the original equation, we looked at the wave, and that most people find that most natural. But in this second expression, we're looking at the circular motion equivalent. So if I have a point here, that is like going around once and then going a little bit more. You know, that point there is like that point there, and that point there is like that point there. And it's getting used to, as x is bigger, so you go around, and as t is bigger, so you go back, and that's what this is doing. I don't know if that helps, but anyway, there it is for today. There you have it.